In this lesson, we will delve into the content of Task 1.3 Inches Project 1, which is efficient milling and tool wear. We will first familiarize ourselves with the concepts, characteristics, and applications of efficient milling. Then, we will explore the types, causes, and processes of tool wear. Additionally, we will learn how to measure tool wear and make informed choices regarding the selection and use of tools in efficient milling. Through these topics, you will grasp the technical essentials of efficient milling and methods to address tool wear. Overview of efficient milling. Efficient milling is a machining method that significantly increases the metal removal rate by enhancing parameters such as cutting speed and feed rate, all while ensuring machining quality. It is widely applied in industries such as aerospace and automotive manufacturing. For example, in the aerospace sector, lightweight materials such as aluminum alloys are extensively used to reduce the weight of aircraft. Efficient milling allows for the rapid machining of complex aerospace components, thereby enhancing production efficiency. From the perspective of cutting parameters, efficient milling has specific requirements for cutting speed Vc, feed rate F, and depth of cut AP. The formula for calculating cutting speed Vc is Vc equals pi dn divided by 1000, where d is the tool diameter in millimeters, and n is the tool's rotational speed in revolutions per minute (rpm). Increasing the cutting speed can make the cutting process smoother and reduce cutting forces, but excessively high cutting speeds may lead to increased tool wear. The feed rate F refers to the distance the tool advances per revolution or per tooth. Reasonably increasing the feed rate can enhance the metal removal rate, but it may also affect the surface quality of the machining. The depth of cut AP refers to the thickness of the layer being cut by the tool, and its size directly impacts the cutting force and the machining efficiency. Characteristics and advantages of efficient milling. Efficient milling is characterized by a high metal removal rate and short machining time. Compared to traditional milling, it can complete the same machining tasks in a shorter period. For example, in the machining of automotive engine blocks, the use of efficient milling technology can reduce machining time by 30% to 50%. Additionally, efficient milling can improve the surface quality of the machining, reducing surface roughness. This is because during high-speed cutting, the cutting force is reduced, which in turn decreases the deformation and vibration of the workpiece, resulting in better surface quality. Types of tool wear. Tool wear is primarily categorized into three types: flank wear, crater wear, and edge wear. Crater wear. During the cutting process, intense friction occurs between the chip and the rake face, leading to crater wear on the rake face. This is due to the high temperature and high pressure in the contact area between the chip and the rake face, causing wear mechanisms such as adhesion and diffusion in the tool material. Crater wear is more common when cutting plastic materials at high cutting speeds and with large feed rates. Flank wear. The flank face comes into contact with the machined surface, and under the influence of cutting force and friction, the flank face gradually wears down. The amount of flank wear is usually denoted by Vb. Flank wear affects machining accuracy and surface quality because the increased friction between the worn flank face and the workpiece surface generates more heat, leading to workpiece deformation. Edge wear. Edge wear occurs at the junction between the rake face and the flank face, typically caused by stress concentration and a large temperature gradient at the cutting edge on the workpiece edge. Edge wear can reduce the strength of the tool's cutting edge, making it prone to chipping. Causes of tool wear. The primary causes of tool wear are mechanical wear and chemical wear. Mechanical wear. This includes abrasive wear and adhesive wear. Abrasive wear refers to the hard particles in the chip and the workpiece material, such as carbides, oxides, etc., scratching across the tool surface, creating grooves, and causing the tool material to flake off. Adhesive wear occurs when the chip adheres to the tool surface, under high temperature and pressure. As the chip flows, the adhesion points are torn away, taking tool material with them. Chemical wear. This primarily includes diffusion wear and oxidation wear. Diffusion wear refers to the mutual diffusion of elements between the tool material and the workpiece material at high temperatures, altering the chemical composition and microstructure of the tool material, thereby reducing its hardness and strength. Oxidation wear occurs when the tool material reacts chemically with oxygen in the surrounding medium, forming oxides. These oxides have lower hardness and are easily removed by the chips and workpiece. The process of tool wear. Tool wear is generally divided into 3 stages: the initial wear stage, the steady wear stage, and the rapid wear stage. Initial wear stage. When the tool is first put into use, the micro-level unevenness and the surface roughness of the cutting edge are relatively high. This results in a smaller contact area with the workpiece and chips, leading to higher pressure per unit area and thus a faster wear rate. Steady wear stage. After the initial wear, the micro-level unevenness of the cutting edge improves, increasing the contact area and reducing the pressure per unit area. The wear rate tends to stabilize. In this stage, the amount of tool wear is approximately proportional to the cutting time. Rapid wear stage. Once the tool wear reaches a certain level, the strength and sharpness of the cutting edge significantly decrease, causing the cutting force and cutting temperature to rise sharply, and the wear rate to accelerate rapidly. If the tool is not replaced in time, it will severely affect machining quality and production efficiency. Indicators for measuring tool wear. The main indicators for measuring tool wear are tool durability, 10 tool life L. Tool durability, T, refers to the cutting time elapsed from the start of cutting until the wear amount reaches the dullness standard. The dullness standard is usually determined based on machining requirements and the tool material. For example, in general milling operations, the tool is considered to have reached the dullness standard when the flank wear VB reaches 0.3 to 0.6 mm. Tool life L refers to the total cutting time from when a new tool begins to be used until it is completely worn out. It is equal to the tool durability multiplied by the number of times the tool is resharpened. Rational selection and use of tools in high-efficiency milling. In high-efficiency milling, the rational selection of tools is crucial. Tool materials should possess high hardness, high wear resistance, high heat resistance, and good chemical stability. Common tool materials include high-speed steel, cemented carbide, ceramics, and cubic boron nitride CBN. High-speed steel tools. These tools have good toughness and cutting performance, making them suitable for milling operations with low cutting speed requirements and complex shapes, such as cavity milling in mold manufacturing, cemented carbide tools. These tools offer higher hardness and wear resistance, as well as good heat resistance, allowing them to withstand higher cutting speeds. Cemented carbide tools are the most widely used in high-efficiency milling and can be used for machining various metal materials. Ceramic tools. These tools have extremely high hardness and heat resistance, allowing them to perform machining at very high cutting speeds, though they have relatively poor toughness. They are suitable for machining high-hardness materials such as hardened steel. Cubic boron nitride (CBN) tools with hardness second only to diamond. CBN tools offer excellent wear resistance and heat resistance. They are primarily used for machining high-hardness, iron-based alloys and nickel-based alloys. The geometric parameters of the tool also affect the effectiveness of high-efficiency milling. For example, increasing the rake angle, gamma 0, can reduce cutting force and cutting power, but it will decrease the strength of the tool. Increasing the clearance angle, alpha 0, can reduce friction between the flank face and the workpiece surface, but an excessively large clearance angle can worsen the tool's heat dissipation conditions. Therefore, it is necessary to select the tool's geometric parameters reasonably based on the specific machining conditions. During the use of tools, attention must be paid to the clamping accuracy and dynamic balance of the tool. In precision milling, there are almost stringent requirements for the dynamic balance and the clamping accuracy of the tool system. If the tool is not clamped securely or lacks proper dynamic balance, it can cause vibrations during the cutting process, affecting machining accuracy and surface quality and accelerating tool wear. This requires us to meticulously perform tool clamping and adjustment during the operation, striving for ultimate precision and embodying the spirit of craftsmanship in pursuit of excellence. Case study. Taking the machining of aircraft engine blades as an example, the blade materials are usually difficult to machine materials, like titanium alloys, with complex shapes and high precision requirements. By employing high-efficiency milling technology, selecting appropriate cemented carbide tools, and choosing reasonable cutting parameters, machining efficiency and quality can be significantly improved. During the machining process, it is important to closely monitor tool wear and replace the tool promptly when wear reaches a certain level to ensure the machining precision of the blades. Additionally, during tool clamping and adjustment, clamping accuracy and dynamic balance must be strictly controlled to ensure the stability of the machining process. In this lesson, we focus on high-efficiency milling and tool wear. We first explored the concept, characteristics, and advantages of high-efficiency milling and learned how to calculate and select cutting parameters. Then, we studied the types, causes, and processes of tool wear and clarified the indicators for measuring tool wear. Finally, we discussed the rational selection and use of tools in high-efficiency milling, including the choice of tool materials and the geometric parameters, as well as the importance of tool clamping and dynamic balance. Through case analysis, we gained a deeper understanding of the application of high-efficiency milling technology in actual production. I hope that in your future studies and practice, you will strive for excellence, pay attention to technical details, and continuously improve your professional skills.